Thank you very much, Giacomo, for inviting. It's nice to be in Torino, even virtually. So the talk will start with some background material on repetitive control and internal model principle in general. The main ideas will be discussed in the second part, followed by some simple academic demonstrations. And implementation issues will be discussed after that, and then concluding remarks will finish it. So I would like to start with really beginning. So it's some prototype control problem, quite stripped down, but still representative in the context of the today talk. Let's say we have some plant, P, and we have its output, which is also a regulated signal. We would like to control it. The means of our control is control input to U, which we can change as we wish. But there is another input, let's call it disturbance, D, which represents our connection with the outside world. And our goal is to keep Y close to what is called the reference signal, which represents our requirements for some class wide enough of reference signals and disturbances, despite those disturbances. So, of course, it is very easy to come up with this control law, which we can refer to as our dream control law. What we shall do is just to process our reference signal by the inverse of the plant and subtract also the disturbance signal, in which case it's easy to see is that the output will be exactly R. But of course, this control law is not quite practical because it requires very good knowledge of the model of the plant. It needs also stable invertibility of the plant and the implementability of this inverse system. And we also need to measure the disturbance, which is normally not what we can do. Then we need to have enough control resources, etc., but those reasons are enough in this context. So it looks like an impossible problem, but in fact, we can conceptually at least achieve it by the use of feedback. Consider this standard unity feedback configuration where we now use some controller. We try to design a controller K to achieve the goal. This unity feedback system is completely described by 4 closed-loop transfer functions: the sensitivity, the complementary sensitivity, the disturbance sensitivity, and the control sensitivity, which describe the relation between external signals R and D and the tracking error, which is the difference between R and Y. We would like to keep it as small as possible, and our control signal, okay? So a nice thing about this configuration is, again, it's a more conceptual view on it, is that if we increase the gain of the controller in whatever sense, we will have that the sensitivity function will vanish. The disturbance sensitivity function will vanish as well because the denominator will go to infinity. The control sensitivity will approach 1 over P, and the complementary sensitivity will approach 1. In this case, in closed loop, our control signal will approach our dream control trajectory. It's 1 over PR minus D. And then we can guarantee all our control goals. And what is remarkable about this is that we invert the plant and measure disturbance without actually knowing the plant model and without having a sensor measuring D directly. Well, this sounds like a dream, but it's also not very practical. And 2 main reasons are stability and measurement noise sensitivity. Perhaps it's safe to say that there are no systems for which this control law, infinite gain, will produce a stable closed-loop system. And the presence of measurement noise here will be greatly amplified, especially in the control trajectory, which is not acceptable. But still, this concept is quite useful because there are many control algorithms which are trying to relax those requirements or other requirements and still keep with this logic in order to get good control. And one of the examples of this is the regulator problem. In the regulator problem, we consider more or less the same setup, and we try to design a controller which now guarantees only an asymptotic tracking of the reference trajectory and rejection of disturbances for some reference and disturbance signals from a known class. And normally it's quite a narrow known class, in which case the problem becomes much more practical. A very good example of it is the use of the integral action in the control. If we know that our reference and disturbance signals are constant or very close to that, then it is known that if we introduce an integral action into the controller, we can asymptotically track any such signal without knowing its actual amplitude, and we can asymptotically reject any such disturbance also without knowing its amplitude. And the rationale behind this is, of course, infinite controller gain, although now it is not an infinite gain, not uniformly infinite gain, but only an infinite gain at a given frequency, in this case, a zero frequency, which is exactly the dominant frequency of our reference and disturbance signals. So, and by the way, it can be also seen in the closed loop transfer functions where both sensitivity and the disturbance sensitivity have zeros at the origin, meaning that they have zero DC gains. Another way to interpret this property, this nice property of the integral action, is to consider it as a model of our reference and disturbance signals, because the Laplace transforms of R, constant R and constant D include a pole at the origin. So exactly the same pole at the origin should be added to our controller. And this is the base of the celebrated internal model principle, which can be where this idea can be extended to a much wider class of signals. Namely, it says that all unstable poles of the Laplace transforms on the reference and disturbance signals must be a part of the controller. So in a sense, controller should contain a model of the external world. In this case, the problem is solvable, perfectly solvable, if there are no cancellations, unstable cancellations between the model and the plant, and if K stabilizes the augmented plant MP. And again, the rationale behind this is that with this choice, we will have an infinite controller gain at required frequencies. A good example of this internal model principle is the rejection of harmonic low disturbances. If we have D as a single harmonic signal with a known frequency omega naught, then its Laplace transform has two unstable poles on the imaginary axis at plus minus j omega naught. And then if we include those unstable poles into the model and into our controller, we can asymptotically reject any such disturbance. But, well, and we can, of course, do it for two harmonic signals, three harmonic signals, etc. But in many situations, we have a more rich class of signals to deal with. And I would like to illustrate this by this nice example from the group at Eindhoven. It is a concept of the kind of new generation of high precision printers. And if we consider classical printing, printers that we all know, then the head of the printer has very simple horizontal motions with constant speed, and the media proceeds stepwise, which is quite problematic mechanically because those stepwise transportation introduce quite a lot of nonlinearities which are hard to overcome. An alternative is to use a continuous media movement, which is much easier to guarantee. But then in order to print, we need more sophisticated movements of the printer head, like in this animation. So as you can see, we need to have it following some periodic trajectory. But then many mechanical problems can be alleviated, and then performance of such printing can be improved. And there are many more applications where what we need is either to follow some periodic trajectories, which are not just one or two elementary harmonic signals, or reject such class of disturbances. And the repetitive control is exactly aiming at solving the regulator problem for arbitrary periodic reference and disturbance signals for a given period tau. The rationale behind, or why can we do this, is just because, well, at least a way to think about it is just consider the Fourier transform of any, let's say, smooth enough periodic tau periodic signal. It is a superposition of an infinite number of elementary harmonic components, which are integer multiples of the fundamental frequency of this period, which is 2 pi over tau. So then what we need is to build a controller which has an infinite gain, and each one of those pure imaginary points, j omega I, okay? It sounds like a mess, but about 40 years ago, Inoue, Nakano, and Iwai proposed a very elegant and nice way to implement such kind of controller. What they suggested is to introduce a delay element as a feedback interconnection of the controller. In this case, so this is effectively our model, 1 over 1 minus delay, and it's not hard to see is that this model contains, has an infinite number of pure imaginary poles exactly at points that we need, which are 2 pi over tau times some integer I. And if we incorporate such an internal model into our control system, then it's not hard to see is that the sensitivity and the disturbance sensitivity transfer functions will have zeros at exactly those points, meaning indeed that we will asymptotically reject any periodic disturbance and track any periodic reference signal with this frequency. So it sounds too good to be true, and indeed there is a catch, and catch is the stability analysis here. Let's consider this system. Our goal is to design a controller K which stabilizes the whole loop. And if we'll consider the characteristic equation of this system, which will be in this form or equivalently can be presented in this form, it is probably not hard to see that this characteristic equation is the same as the characteristic equation of the standard unity feedback configuration with the loop, which is the nominal sensitivity, which is the sensitivity function of the loop with only P and K, and a loop delay. This is a more conventional system to analyze, and then it is known that this system is practically impossible to stabilize. And the reason is that if the transfer function P times K is strictly proper, and this is a reasonable thing to assume, then the high frequency gain of this equivalent loop will be exactly 1. And exactly 1 means that it is not strictly contractive, and strict contractivity of the high frequency loop gain is a necessary condition for the existence of a practically stabilizing controller. This is a notion of W stability introduced by George and Smith some years ago, okay? Which means that in probably any reasonable situation, we have no hope to design a stabilizing controller for this system. So how can we work around this situation? Standard trick in repetitive control is to introduce some additional filter in the repetitive block. This filter might be any stable system, but the requirement is that its high frequency gain should be strictly contractive. In this case, the equivalent loop will be the same as before with the addition of this F, and then the high frequency gain of this equivalent loop is exactly the high frequency gain of F. And if it's strictly contractive, then the stabilizing controller always exists. So then potentially, at least we know that the problem is solvable. But of course, this is no longer our original repetitive loop. So we lose effectively the ability to reject any periodic disturbance and track any periodic R, because just in order to do that, we need to guarantee that at every frequency in the Fourier series expansion, the frequency response of the filter is exactly 1, which, taken into account this high frequency gain requirement, is never possible. Okay. But still, this is a reasonable workaround just because in principle, we never need to track an arbitrary periodic signal. We always work with some low frequency signals, and there is no sense to try to reject every periodic disturbance because high frequency components of D are rejected by plant anyway, if it's low pass. So if we concentrate only on low frequency signals, relatively slow periodic signals, then what we need is to guarantee that the frequency response of f is 1 or very close to 1 at sufficiently large number of indices, number of frequencies. And this can be done. So just designing a low pass f with a high nav bandwidth could do the trick. And then we can have maybe not perfect, but very good regulation for all slow tau periodic disturbances and reference signals, which is a reasonable solution. So the name of the game here is to choose a high bandwidth, low pass filter F for which a stabilizing controller can be designed. And high bandwidth we need in order to increase the number of frequencies for which the gain of this controller will be high enough to reject them. This is still a non-trivial problem because this is an infinite dimensional system which includes a delay in quite a non-conventional way. It's not just a loop delay for which dead time compensation ideas can be used. It's something more involved. So probably it's safe to say that the literature on repetitive control is dominated almost exclusively by robustness arguments. Namely, if we consider this equivalent loop interpretation that we used before, if we guarantee that the loop gain is strictly contractive at all frequencies, then by the small gain arguments, we have the closed loop stability, which means that what we can do, we can try to design K in order to guarantee that the H infinity norm of this weighted sensitivity, by the way, it does not depend on the delay. Delay does not affect this gain, is strictly smaller than 1. This is a standard weighted sensitivity H infinity problem, and thus can be designed by standard tools, which is a good news here. But this is an obvious overkill, because if this condition, this small gain condition holds true, so then system will be stable for all possible delays tau. We don't need it. Tau is not a part of our problem. Tau is a part of our solution, which we do know. So we don't need to design controller for all possible tau. This design is potentially restrictive, and it's quite not clear what kind of restrictions those conditions impose on set of possible stabilizing controllers. And it's not quite easy to incorporate transient analysis into this approach. Okay. So in this talk, I'll put forward an alternative approach, which is simple, perhaps surprisingly simple. It is absolutely non-restrictive, and it results in an easily implementable controller K. And the main idea behind this approach is the loop shifting. Loop shifting is a very old idea. One can see this idea already explicitly in the celebrated 66 paper by George Zames, but some refer even to some earlier sources for this. And the idea is like this. Let's assume that we have the feedback interconnection of two systems, G1 and G2. Internal stability in this case is equivalent to the stability of 4 closed loop transfer functions from V1 and V2 to Y and U. And now, well, this is a standard configuration, and in many situations, properties of G1 and G2 might not be quite nice or easy to deal with. So the Zames suggested to do the following trick. Let's add and subtract the very same system pi to this loop. And now let's try to combine the upper pi with G1 and the lower pi with G2. By the way, this changes nothing, right, in terms of our loop. So with some simple block diagram algebra, we can move those blocks. Important is that by moving this point from here to here, we need to introduce this additional signal. It, of course, can be combined with V1. So then we have this interconnection, and now it is in more or less the same form as we had before with the new G1 and new G2, but those two signals are different from the original signals, V1 tilde and Y tilde. They depend on pi, which means that in order to keep internal stability, we need to have stable pi. So apart from this, this is an absolute arbitrary pi, and we can use any pi without altering the stability property. So then combining them, we have the original configuration with different systems. And those two different systems, G1 tilde and G2 tilde, might have some favorable properties which are easier to analyze. It was used for years in analysis. For example, if G1, we would like to use some passivity tools. If G1 is not passive, so we can add some positive system to it, making it passive, and then need to compensate it by kind of more complicated controller. Circle criterion can be derived through those kind of tricks, etc., etc. So this is really a well-known tool in the analysis. And it is used actually in the design, maybe without an explicit mention, but a very good example, in my opinion, is a Smith controller, Smith predictor. Because if we have a dead time plant, which is a finite dimensional plant and delay, it can always be decomposed as a parallel interconnection of the delay-free plant and pi, where pi is the system. So if P is stable, this pi is a legitimate candidate for loop shifting. So then this is our plant. If we just shift our loop, move this pi to the controller, we'll have this Smith predictor configuration. Because now what we need is to design this controller for the delay-free plant and then implement it with a pi block in its feedback, okay? And of course, if P is unstable, this idea cannot be used directly, but there are modifications of the Smith predictor, like Watanabe and Ito modified Smith predictor that do more or less the same trick, but with little more sophistication. So it can be done. Now let's return to our repetitive configuration with the repetitive element here. And a key observation is that our augmented plant, which is P and the model and the repetitive element, can always be presented as the feedback interconnection of P itself and some delayed G, where G is the ratio between the filter F and the plant transfer function P. Okay, so this is just a straightforward algebra to check it. And then if G is stable, of course there is a big if here and we'll discuss it later on. If G is stable, we can shift this loop. We can just shift this G delayed to the controller part and end up immediately with a result saying that the controller K stabilizes augmented plant PM if and only if K minus G delayed stabilizes the original finite dimensional delay-free plant, which means that we can reduce the original problem of designing K for a very complicated system to an equivalent problem of designing a new controller for a delay-free plant P. And then this is the whole procedure. Design some K tilde for P, and then implement our controller as K tilde plus G delayed, which is really simple. Okay. So checking the closed loop transfer function sensitivity and the disturbance sensitivity. If you remember, originally we had delays in their denominators, which is hard to analyze, but we needed it in order to have required zeros of S and TD. With this trick, those functions still have zeros at points where we need, but now their denominators, characteristic functions, are completely delay-free. So we reduce the problem to an equivalent delay-free problem, keeping required properties of the repetitive element. It is interesting to compare this trick with classical dead time compensation like Smith predictor, and we can see some kind of duality here. In the dead time compensation, we normally present the plant as a parallel interconnection of a finite dimensional, easy to control plant and an infinite dimensional block pi, when then pi appeared as a feedback part interconnection with the controller. In the repetitive control, we have a feedback interconnection in the plant, which will result in the parallel interconnection in the controller. But in both cases, we have delay-free designs as design part of the controller, in the controller design part, okay? Okay, so then let's return to the question, where is this G stable? Because this is a key ingredient here. Because G is a ratio between F and P, it's easy to see that it will be stable if every unstable zero of P is also a zero of F. In this case, they're canceled out and G is stable. And pole excess of F is at least as big as the pole excess of P. The second assumption is condition is not quite restrictive. We can always introduce additional poles into the filter at sufficiently high frequencies. But the first one might be. But if the plant is minimum phase, there is absolutely no restriction. So for minimum phase plants, which is again some duality with a Smith predictor works for stable plants, this scheme works for minimum phase plants, we can easily do that. If plant is non-minimum phase, there are two possible workarounds here. The first one, the spirit of it is more or less like the modified Smith predictor. Instead of looking for the feedback representation of our original augmented plant as the same plant and some stable element, we can look for a finite dimensional system P tilde, which is different from the plant, but still finite dimensional, and look for its this representation of the original system. And it happens that we can always find P tilde, finite dimensional one, for which this is possible. It solves this problem, so details here are not so important, but just this problem is always possible to solve, which means that we can always apply the same trick, and then the design procedure will be just a little bit different. First, we need to design K tilde for a delay-free P tilde, which is different from our plan, but still finite dimensional, and then implement K as K tilde plus pi. A problem here is that this pi might be quite hard to implement. If the plant is non-minimum phase, normally this pi will be kind of distributed delay system, which needs to be approximated in order to be implemented. Such kind of systems appear in smoothing, in fixed leg smoothing problems, and in dead time compensation. So in principle, we know how to implement them, but there is one difference that makes the use of this idea in repetitive control more involved. Namely, in smoothing and dead time compensation, we normally need to approximate pi in the low frequency range, which is quite easy to do. Repetitive control intentionally uses high frequency gains at high frequencies, so sufficiently high frequencies. So we need to extend the frequency range in which the approximations of P will be good enough, which might not be quite a trivial problem, okay? Still, I think it's still quite open. Another workaround would be to introduce the same non-minimum phase zeros of P as zeros of F. Technically, this is very simple to do, of course, and then we can easily implement such kind of controllers because then G will be automatically stable. But if we remember, we would like to keep F, the frequency response of F, as close to 1 as possible at certain frequencies of interest. And if we add non-minimum phase zeros to F, this task might be more involved. For example, we can find some lower bounds on, well, this H-infinity kind of problem can be used to solve this, and then there are hard bounds on the accuracy of such kind of approximation, okay? A possible solution here is to use non-causal filters. And this is actually ideas that is used for many years in repetitive control for different purposes, but still this is idea. The trick is that we don't need to implement F itself. We need to implement the delayed F in the repetitive element. So then we can relax to a little bit causality of F. And we can implement like kind of design F with some prediction elements, which are still smaller than the delay then the period of signals that we need to track, and then we can improve those bounds, and then we can have much better repetitive properties. Okay, so this is another idea how to do it. So to illustrate this, I'll consider a couple of very simple academic examples. So the setup is standard. I just consider only disturbance attenuation here, and let's assume that we choose the first order low pass filter as f. Omega 1 is exactly the fundamental frequency of our period, 2 pi over tau, and alpha is a tuning parameter. So the larger alpha is, the higher the bandwidth of this filter. And in this case, we can even analytically get the mismatch between the frequency response of f at frequencies omega I and 1. Okay, this is a function, this is a simple function, and those two plots represent those gains at different omega i's, for two values of alpha, so big alpha and small alpha, okay? And if we need to have this difference smaller than certain epsilon, it's quite easy to see that the larger alpha is, the more frequencies we can squeeze into our precision, okay? So this is quite simple. So we have alpha as a tuning parameter. We would like to increase it in order to make more and more frequencies, high gain at more and more frequencies of interest, okay? So let's start with a minimum phase plant. I take just a simple integrator. In this case, f over p will be this high pass filter, which is obviously stable. So then we can design a controller for the integrator itself. This is a simple task. We can use a proportional gain, and then the overall controller will be proportional gain plus g delayed, which is easy to implement. And then let's say if we choose alpha as 10 and apply a square wave disturbance, we can see that from 0 to tau, when initial conditions are 0, the system is did not learn the periodic disturbance yet. We have quite poor behavior, but then it converges quite rapidly to some steady state value. And here we can see that residuals are quite high. I intentionally picked a square wave because this signal has substantial high frequency components. So just to illustrate what we'll need to do. So this alpha is not enough, and we have quite a lot of residuals. But if we increase alpha and it does not require any change in the control design, we can see that the residual oscillations getting smaller, or if we go to 1000, they're practically invisible. So we indeed have the almost perfect rejection of these kind of disturbances. And the same works for the sawtooth. So increasing alpha will get better results. Another example is harder. This one is a non-minimum phase. We have 1, 0 at +1, and also unstable. We have a pole in the right half plane where p is from 0 to 1. I picked it to illustrate that in this case, the robustness-based design might fail, because the sensitivity, the weighted sensitivity problem to be solved here is known to be lower. The attainable H-infinity norm is lower bounded by this expression. And if we would like to keep it strictly contractive, we need to keep alpha smaller than this value. So if p is close enough to 1, so we have close poles and zeros, there is probably no chance to have some reasonable alpha out of this procedure at all. But the proposed procedure does not have these limitations at all. So we consider G, the G is indeed unstable, F over P, yeah? So we need to do something else. And it's quite convenient to split it into two parts, just by partial fraction expansion. So everything stable put to this part. It need not be approximated, it can be kept as is. And this part need to be approximated. We need to design a new p tilde, for which the block pi will be stable. And it happens that in this case, p tilde will be almost the same as the original plant. The only difference is that we need to replace our original pole at p with another pole at p tilde. This is an analytic expression for it. But what's important is that it is always larger than p and always smaller than 1, than the 0. Okay, so we have yet another plant having more or less the same structure as the original plant, probably a little harder to control, expectably, And then we have this pi block where this is distributed delay element which need to be approximated. But putting the implementation aside, the design then is quite simple. Because for this plant, we can design our controller quite easily. And in fact, if I pick P as 0.8, in the whole range of alpha, which we considered before, P tilde will be just a little bit larger than P. So it's really about 1%, up to up percent deviation from the original P, which means that we can design a single controller. This, by the way, P tilde does depend on alpha. So if we'd like to play with alpha, we'll end up with different P tilde plants. But in this case, one single controller does the job for every one of those P tilde. This is just a lead controller. And as you can see, it does the job and more or less with the same pattern as in the minimum phase case. So for alpha 10, it is we have quite visible residuals. So for 100, they are lower. For 1000, they are practically invisible on this plot. And the same with the SO2. So we can design controllers here quite easily. So a couple of words about the implementation, at least in the minimum phase case when G is stable. In the design part, the repetitive element was augmented to the plant. So we designed our controller K, or one part of the controller, for an artificial plant that includes also repetitive element. Then, after the controller is designed, we need to add the repetitive element to the controller because it's a part of it. So in this case, the actual controller will be of this form. So this is our repetitive element, and this is the K tilde design for our plant, and this is the element that compensates the delay. First of all, as we can see, there are two delays here, and obviously it would be advantageous to use only one delay because it's, even though we implement it, but we would like to implement it as one block. It can be easily moved to this point, of course, just to make it one delay. I prefer to do it a little different way. I prefer to represent this controller as linear fractional transformation of some finite dimensional parts and the delay here. I would like to do it this way just because then when I plug this controller into the plant, first I can do all manipulations with the finite dimensional parts, keeping still this delay outside of the manipulations of the loop. And this is easy to do. The details are not quite important here with the star product notions or whatever star product notion, etc., etc. Important is that we'll end up with another linear fractional representation of the closed loop system where delay is in feedback and the 2-2 part of the generator of those closed loop systems is 0. Well, if we just write it down in a more conventional way, we'll see the formulas that we already know. But what I would like to emphasize here is that these manipulations allow us to look at little different kind of controller. We can take the very same generator here, but put some other block delta here, which is not necessarily our delay. The same manipulations apply here, and we'll end up with a closed loop system. Delta appears quite nicely only in the numerator, like kind of affecting only zeros of the system. Why can we need to use such kind of controller? For example, if we need some adaptation. Let's say that the period of our disturbance is drifting, and we would like to adjust our controller to changing period. We can do it, of course, with many adaptive schemes, but as we know, adaptive control, especially when we adapt some delay part in it, might be extremely sensitive to such kind of adjustments. In this situation, as long as we have delta block stable, the closed loop system remains stable. And if delta here is a time-varying delay, so there are kind of standard conditions, at least sufficient conditions for the stability of this time-varying delay element, is that its derivative is strictly contractive, which can be thought of in terms of slow adaptation, right? So any slow adaptation here will keep the closed loop system stable, which is quite nice, I think. We don't need to worry about the closed loop stability, even changing our delay. So to conclude, a novel transformation to deal with repetitive control has been proposed. Its key point is that it reduces the stabilization of the original repetitive control loop to the stabilization of repetitive control-free loops, finite dimensional loops. This approach is completely non-restrictive, so in no place in those transformations any restrictive assumptions were introduced, meaning that we can parameterize all stabilizing controllers here. We can then analyze transients, we can analyze robustness, etc., without thinking about what kind of restrictions we introduced. And the implementation of this scheme, at least in the case of the minimum phase plant, can be done easily and efficiently. Possible extensions would involve implementation issues for non-minimum phase systems, systematic use of non-causal elements, MIMO problems, multi-period repetitive control, robustness adaptation, etc., etc.